Hey everybody, it's Ripley back again. We're going to talk about partial derivatives today, and these are super cool. Um, Truthfully, the computation of them is not very difficult. However, it's important to understand what you're doing when you're taking a partial derivative of a curve, all right, a curve in space. Because let's say, for example, let's say that z equals x squared y plus sine xy squared, which is equal to f of xy, right? Hopefully we're relatively comfortable with this notation. I don't know what that little scrub dot's doing there, but let's get rid of that. So let's think about what's happening here. This is a fantastic little figure to understand what's going on. So what do we have? We have a curve in space, right? We got x, we got y, and then we got z popping up here. And then what we're doing in this case is we're cutting through the figure with the plane y equals 1. All right, now look close. What is this little blue line? Well, this blue line is the line tangent to the figure that's in the plane y equals 1. Right? Now, why would that be useful? Well, we'll get into that, but hopefully you can sort of see why that would be useful, kind of what it does on what it's going to tell us about the plane. And later on down the road, we're going to have a whole lot of use for partial derivatives as well. But right now, I just want to sort of give an introductory understanding of how partial derivatives work geometrically. We could also just as easily fix the plane at x equals 1, which would chop through the figure. Oops, I lost my thing. I guess I can't write on that, can I? Which would chop through the figure along the plane x equals 1, and then there would be a line tangent to the curve that was in that plane. All right, so let me blow this thing up, and I'll show you how to take these derivatives. Super easy. The first thing that you need to know is notation, because there's lots of notations around this. Partial derivatives can be defined in this way. So this is the notation. So you might see this depending on the text, depending on the author. If z equals f of xy, one way to write a partial derivative is the partial derivative of x with respect to x, of xy. Another way is to write this as f with a little subscript x right there. The most common notation is this little delta thing, all right, of f, so over delta x. Now, these aren't technically the same deltas. What they mean is partial derivatives. It's like we're lazy and we're not doing a full d. It's this, and it's not d like that, like we're used to writing, because we know if it were df, we know that y prime, f prime of x, equals y prime equals df over dx. This tells us that we're dealing with partials, okay? Another way to write this, and we've seen the notation before, remember this guy? D over dx of f of x. Well, we can just as easily write it like d over dx, over dx of f of xy. Now, we're going to get into some sort of anachronistic notations as well. Sometimes you'll see this as dz over dx. That tells, since since z equals f of xy, we could say partial derivative of z with respect to x. Sometimes you'll see this as f of 1. Sometimes you'll see this as d1 of f. Sometimes you'll see this as dx of f. Look, I'm going to use this notation, I'm going to use this notation, and every now and then that notation may squirt out, all right? Similarly, and I'm not going to go through the whole thing, I'll just give you the basic notations. If I write this guy, then this is going to be f sub y df over dy, partial f over partial y, right? Those are going to be the primary notations that you'll see. All right, so now you got the notation. So at least when you see these little squiggly d's, the squiggly d, it's kind of fun to say. When you see those, you know that you're taking partials. So let's figure out how to do it. All right, I'm going to take df, or partial f over partial x, all right, of this function. Now, it's so amazingly simple, but it can get pretty convoluted. So you really do have to sort of slow yourself down and go to your happy place. Here's the way it works. It simply takes z, and anything that ain't an x, it treats as a constant, which is awesome. So it's along for the ride. Now, I know I've been pounding into your brain that the derivative of constants are zeros, but we're not afraid of that, right? Remember when y equaled 3x squared? Well, this implied that y prime equals 3 times 2x, which is 6x, or I could just say 6x. True? So we need to be aware that these constants, when we treat them as constants, are just along for the ride. So let's do this one. All right, I'm going to change colors. I'm going to change colors. All right, this guy is a constant. This guy is a constant. That's a variable, and that's a variable. Remember, chain rule is always in full effect. So when I go to take the derivative, this is 2xy, right? That y is a constant, so it's along for the ride. Plus, now you ready? This is the sine of blah. Well, the derivative of sine of blah is cosine of blah times the derivative of what's inside. Well, what's the derivative of what's inside? Remember, this guy's a constant. That's the variable that we're taking the derivative of. So this just turns into y squared. If I want to do partial f over partial x, which I just did, that would be ludicrous to do it all over again. Let's make that a y instead. Then this guy would be what? Okay, now let me change colors again. Let's go to red. Now this guy is a constant, and this is a variable, and this guy is a constant, and that's a variable. So let's see how that changes things. All right, well, here we go. What would I get? If this is a constant and this is a variable, the derivative of y is 1, so I just get x squared, plus, now here we go again, sine of blah. The derivative of sine of blah is cosine of blah, which is just x, y squared, times, now it's a little trickier, but not much. That's a constant. What's the derivative of y squared? I get 2xy, and I'm done. It's literally all you have to do ever, which on the face of it seems ridiculously easy. But let's make sure that we understand what we're doing, and we'll refer back to that graph in just a sec. Remember, we don't just take these derivatives. We want to evaluate them at a point. So let's say, just for giggles, that I want to do df over dy at the point 1, 1. Now, what this is saying is we are fixing our curve at x equals 1, that plane. All right? That's what we're doing. So that is going to equal, if I go to this guy, this is going to be 1 squared plus the cosine of 1 times 1 squared times 2 times 1 times 1. So this just turns into 1 plus 2 cosine of 1. Similarly, if I do df, that's supposed to be partial f over partial x at the same point. Now what I'm doing is I'm fixing y equals 1 as the plane. So that's very much like this case. We fix, now clearly this curve and the curve that's defined by the function that I was playing with, they're not going to be the same thing, right? However, it's the same idea. You fix y equals 1, you chop the plane, and then you evaluate x at that point. So this is just going to be, I got to figure out what's going on here as far as my partial of x. Let's see, that's going to be 2 times 1 times 1 plus cosine of 1 times 1 times 1. Whoops, let's put a 1 squared there. And I end up with 2 plus cos 1, which is a little strange how they flip like that. Now, what does that say? What are these? Remember, these guys are just slopes. What are they the slopes of? Well, back to this. They're the slopes of that line tangent when the plane cuts through the figure. It works exactly the same way that slope work in a plane. In fact, if you think about it, what we've done is we've sort of cheated. We've said, well, finding which derivative are we going to find? What are we doing here? Well, screw it. What we'll do is we'll chop it with a plane, and then we'll just sort of go back to old school planar derivatives. Makes our lives easier. However, you see, as is the case in this figure as well, had I cut it at x equals 1 and then looked at it at y equals 1, then I would have had a very different tangent line. Like in this case, what did we do? We cut it with y equals 1 and then we went over to x equals 1, and that kind of got us relatively close to this, right? I mean, I'm assuming that the scales are not preserved, right? All right, so that's how partial derivatives work. They're not difficult at all. You just got to make sure that you understand graphically what's going on, which I'm not going to lie to you, I still struggle with because it's difficult for me to visualize what these things look like. And that's why we have all these graphing utilities, which are very, very helpful. Now, what we're going to do now is we're going to talk about higher order derivatives, higher order partial derivatives, which can get a little crazy, but trust me, they're not very difficult. I'll see you here. I'll see you back in just a second. One thing I wanted to mention before we move on is this can happen. We can take partial derivatives at even higher dimensions. So let's say we had some god-awful alpha equals f of x, y, z, beta, gamma, right? Just some awful thing. The partial derivatives would work exactly the same thing. If I took the partial of alpha with respect to x, then anything that's not an x is just a constant. So I treat it exactly the same way as I would any other variable, or any other partial derivative. It's very, very simple to work with. Now, let's talk about higher order. All right, so higher order derivatives. Let's go higher order partials. You guys are going to have to yell at me if I use derivatives in place of partials. Okay, you ready? So I'm going to get a little simpler this time, if you guys don't mind, because otherwise all hell's sort of going to break loose on us. Let's do, what should we do this? Oh, let's call f of x, y. So I can use both notations, which is kind of helpful. Let's call this, how about x squared y plus e to the x y. Okay, let's do that. No, let's just call it e to the y, just cause. Okay. All right. What's the domain? What's the domain of this function? Well, hopefully you see that the domain is equal to, we want to be really fancy, the set of all x, y, such that x, y is in R2. In other words, it's all reals. Remember? We could also write this as negative infinity to infinity cross negative infinity to infinity, which means hand me any x, any y, and I can stuff it into this function, and I will get a value out. Okay? Now, let's take the first order partial derivatives. So I'm going to take the partial of y, which with respect to x. Okay, here we go. Remember, this is also referred to as this script f with a lowercase x. You don't have to worry about trying to make that thing fancy. Well, what does that mean? If it's a y, it's a constant. So there's a constant and there's a constant. So when I take the derivative of this, there's my variable, right? My independent variables, those always match up. I get 2xy plus 0, right? That's just a constant. Now, how about this? If I do the derivative, I said the derivative of y as opposed to, you getting those habits, man. Even I do it. And I'm going to pop you for that, and you can scream and yell at me for it as well. All right, if I take the partial of f with respect to y, now another way to write this is fy. It's a little lower, this subscript y. Now, how's that change it? Well, here we go. Now, x is the constant, and y is the independent variable. So this simply becomes x squared plus, well, what's the derivative of e to the y? It's just e to the y. Easy peasy. Okay, now think about this for a sec. How do I take a second derivative? So if I want to take a second partial, what does that entail, right? Am I taking the derivative of the first derivative with respect to x? Or am I taking the partial of the first partial with respect to y? And see what I did there? I changed it. Likewise, which one am I playing ball on? Well, there's a notation that tells us how to do this. All right. Theoretically, if I want the partial exclusively with respect to x, so I'm looking at things like concavity. Remember how these things work. If I'm doing it with respect to x, I am fixing the y value at a certain value, and then I'm plugging in the x value, okay? So be careful with that. You still have to remember how these things behave, okay? So theoretically, what we're looking for are things that are helpful. So remember our notation for a second derivative, right? We had f double prime is equal to, see, now you get in the habit, is d2f over dx squared, and that gave us concavity, right? CC up, CCD, right? Things like that. So let's think about this for a second. What would the 2f over dx squared b. Now what that's telling me is take the partial with respect to x of the partial with respect to x of the original function, right? Remember, algebraically you can create these things. Well, let's look back at our curve really quickly, okay? All right, there's our curve. Now, I understand this is not the same curve, but here's our tangent line. If I take a second derivative, I'm fixing y at y equals 1. In this case, that would only be if I were plugging in a point something comma 1, a comma 1. Then what would the second derivative tell us? Well, it tells us the same thing as it told us in the original Cartesian plane. It would tell us the concavity. It would tell us whether we were concave up or concave down in the plane y equals 1. It's almost like what we're doing is we're stacking a whole bunch of boards, right, of whiteboards, and then we've got this figure, and we just kind of choose the whiteboard that we want to play on, which is kind of an interesting way of thinking about it. All right, so that's interesting, right? Likewise, we could do the second partial of y. Oh, by the way, this notation is written, you'll love this, is written as, you could probably guess, xx. This thing is going to be written as xy. All right, or try that again, yy, because I'm taking the derivative with respect to y of the derivative with respect to y. I should be saying partial, but I am going to interchange those a little bit because you are taking derivatives. But can you also see that I can take the derivative with respect to x of the derivative that we already took, the partial derivative with respect to y? And what would that give me? Right? If I'm looking at higher order, like what would that look like? And that's where it gets really, really crazy, isn't it? Well, this guy turns into, expectedly, this would be d2f, d delta, well, you know what I mean, partial x. I really got to work on that. However, the way that we write this in that f notation, and I think it's more helpful, is we write it as, okay, we took the first partial with respect to y, and then we took the second partial with respect to x. That notation for me is far more intuitive, so I like to use it better. Likewise, I could take the partial with respect to y of the existing partial with respect to x, and this would turn into this partial squared f over, now it's delta y, delta x. However, remember, again, you can use this notation all you want because I find it far more helpful. I do my little script f, and then I took the first partial with respect to x, and the next partial I'm going to take with respect to y. So let's do those. Let's do those really quickly. We've got these, so I'm going to do this f, the second partial with respect to x. Now, see if you can you should be able to just kind of pop it out of your head. Constant, constant. There's the independent variable according to this partial derivative, so I get 2y. Nothing to it. All right, how about this guy? How about this guy down here? Well, constant, let's see, I got to go to this guy. Constant independent variable. So now when I take the derivative of this, this is seen as a constant. It disappears, and I get e to the y. Which is pretty cool. Okay, now here's where it gets a little crazy. You ready? We're going to do x, y first. So notice I start with the partial of x first. That's this one right here. And then I take the partial with respect to y. Well, as far as y is concerned, gone, constant, constant. So I end up with a 2x. And now I'm going to take this guy with respect to x. All right, we'll see what happens. So let's see, start with the first partial. That's this guy. Now we're taking the second partial with respect to x. So anything that's not an x, the partial sees as a constant. That's that guy. Hey, there's our independent variable. And out pops 2x again. That's kind of crazy. That is absolutely circumstantial, by the way. All right, that doesn't really mean anything. However, the fact that they're equal means something, but it's complicated. We're not going to get into that right now. We'll get into that down the road. But for now, let's look at these two guys. These two guys are, the way I write this is partial squared y over partial x squared, and then this guy would be partial squared y. Whoops, damn it. I did that again. Ooh, I just cursed. Ignore that. Damn, like the thing that blocks water. So you do, I mean, I've been teaching math a long time, and you do have to pay attention to what you say and what you write, because they mean different things in different contexts, right? Over delta y squared. All right, and they tell us the concavity of the curve in a fixed plane, in this case in a fixed plane of y, and this guy tells me the concavity of a curve in the fixed plane at x. It works exactly the same as second derivatives. It's just a little more confusing notationally speaking, and you got to pay attention to more variables at once. That, ladies and gentlemen, is partial derivatives and higher order partial derivatives. They're pretty cool. They're super cool. All right, I'll see you tomorrow. Have a